Is Antonella de Ninno. Her title is What We Can Learn About Water from Vibrational Spectroscopy. So please.
Thank you. Thank you to you all and good afternoon. I want to start this presentation starting from a different point of view. I am a physicist, and so I don't know much about all the beautiful things I've learned in these days that are chemomagics are very interesting, but I'm used to look at the spectra in a very simple way. And I hope to show you that even in that way you can obtain many information about the vibrational spectroscopy. Where's the... this way. So this is a summary. I want to start to talk to you about the importance of vibrational spectroscopy because it's very rich of information about the motion of molecules. So it can give us many information about what is really happening inside the sample. And one very interesting point in vibrational spectroscopy is the existence of isosbestic points that are related to the presence of more than one population, independent population in the sample. And applying this technique to water, is it possible to go to the conclusion that water is actually a two-phase liquid? That is, in liquid water at room temperature, you can evidence the presence of two different liquids that obviously share the same thermodynamics because they share the same pressure and temperature, but they have a different energetic content. And then we will see the effect of the solution of salts into the water with respect to the existence of these two different populations. So this is the main spectra of the vibrational spectroscopy in case of water. Here we are in the infrared portion of the spectrum. You can see the wave number going from 1,000 to 4,000 centimeters to -1. And these are the OH stretching vibration and the bending mode at lower energy. The stretching vibration is very rich of information. We'll see how. Water is normally described as a collection of molecules that are kept together by hydrogen bond. We can imagine that one single molecule is related to one or two up to four different water molecules by these very tiny and flickering hydrogen bonds. Or we can imagine that water is made up, there are in water, even a collection of free water molecules that are not related to any other by H bonds. The concept of H bonds is it's a model. We try to describe what we observe by using this very beautiful model that has been introduced by Linus Pauling in the 50s. But what can be explained with the vibrational spectroscopy with a continuum model? That is, a model in which water is represented as a collection of molecules which differs by the numbers of H bonds that each molecule can establish with the others. So in this way we can describe even a long correlation or an average correlation with other molecules. And what can be explained? So the dynamical effects in the line shape can be what we observe. The line shape that we observe in infrared spectroscopy can be explained with a continuum model in terms of dynamical effect. So usually the broad peak that we can observe, the stretching vibration, it's quite broad, it is described in terms of vibration, of a distribution of vibration that is broadened by the thermal collision, and the collision with thermal collision among different molecules. And it's also possible to imagine the existence of non-hydrogen bonded molecules. However, what cannot be explained in terms of a continuum model is the existence of an energy gap that is independent on temperature that can be put in evidence just looking carefully at the data. And another thing that cannot be explained is the effect of solutes on the line shape. This is what is usually done with molecular dynamics simulation. It is assumed that the broadband peak can be fitted with a Gaussian or a Lorentzian or a void function, that are the functions that are usually used when you try to interpolate a spectroscopic peak. But as you can see, the experimental data that are the black one, is not, it doesn't look like a Gaussian. It doesn't look like a void function too. So it's quite difficult to describe what we are observing just with the absorption of a vibration that is broadened by the thermal collision and by the effect of temperature. There is something more behind. This is what happens on changing the temperature. We have seen this figure here many times during these days. As you can see, when you increase the temperature, the peak changes its form. But what is very interesting is that there is a superposition in a certain point that is called isosbestic point, that means equal absorption point, at a certain point that is evidenced by the arrow. So the curves intersect at a certain point. So isosbestic points are generally met when there are two different spaces that are in equilibrium on changing a certain parameter. Here we are changing temperature, and we observe an isosbestic point. So, however, generally speaking, whenever a system is a superposition of two different components and we can change a parameter, we can observe that if the two phases are in equilibrium, one phase decreases and another one increases, but their sum remain constant. The sum of the two components is constant, one decreases and the other increases of the same quantity. This implies a rule of sum. So just looking at the spectrum, we can say that there are two components that are affected in a different way by the temperature. One is decreasing, another one is increasing. So the isosbestic point is a key point. In a continuum model, it is explained from the microscopic character of the fluctuation by a mathematical model. My colleagues say that there is a fluctuation of the vibration that is due to the temperature. They introduce as many parameters in order to fit the function, and they arrive to the conclusion that the isosbestic point is a division in frequency. There is a critical frequency of vibration. Below that, there is one class of vibration, and above that, there is another class of vibration. So they move the problem from the existence of two different species of molecules inside the liquid to the existence of two different classes of frequency. But there are two, anyhow. However, we say that we move the problem to the existence of two different classes of molecules inside water, and we say that if A and B are single chemical species or different phases, we will see in a moment, of a single substance, we can say that A and B, the two species, are in equilibrium, and their concentration is controlled by the running parameter. In this case, is temperature. And we can make another assumption. Let's assume that our system is done by two different populations that are described by the usual relation that related to different states separated by an energy gap delta E. If this is true, we should obtain a Van 't Hoff plot, because if the difference in the energy doesn't depend on temperature, we should obtain a Van 't Hoff plot that has already been shown, that is this one here. And in this case, we observe that Actually, if we want to go through the definition, if I define the constant of equilibrium as the ratio between the two areas, the area above and the area below the isosbestic point, I can obtain a constant equilibrium. I can put it into the Van 't Hoff plot, and I can see what happened. And what happened is that there is a linear relation. So, as you can see, the energy gap between these two phases, or these two populations, doesn't depend on temperature. So, it's not due to the variability due to the fluctuation in temperature. There's something else. So, which is the basic idea that we have about the liquid water? The basic idea is that the ground state, the energetic ground state of the molecules, of an isolated molecule, there should be something more. So when we are describing a collection of water molecules, we have to imagine a different ground state, a physical ground state. How can we describe this ground state? It can be described if we take into account the relation, the change of energy that there are among molecules and electromagnetic fields. So we need a description that is based on quantum electrodynamics. According to quantum electrodynamics, it's possible to imagine the existence of a different ground state of a collection of molecules. And this has a very interesting effect. If we try to imagine the electron cloud of an isolated molecules, we know that it has quite a round shape. It's like a potato, so it doesn't have a particular direction. So it's very difficult to imagine the hydrogen bond in this situation. No preferential direction in the electron cloud. In fact, the hydrogen bond is imagined as a very flickering and very rapid and very faint bond. But in case we want to imagine what happened in case of this different ground state, and we made a calculation, we can find that appears to preferential direction that can be used as a dynamical base of the hydrogen bond model. So what I'm saying that the hydrogen bond cannot be explained if we think at water as a collection of isolated molecules. But it came up from the basic, ab initio calculation, if we assume that molecules are a collection of molecules that are all together, that are described by a common wave function. And so at this point we can try to interpret our spectra. We can try to make convolution of the broadband spectrum in three components. Why three? Because it's the minimum number. We can obviously try to make a convolution using 4, 7. In such a case, the convolution will improve the precision, but they have no more physical meaning. And this is the minimum number of subbands that we can apply in order to obtain a good fit. And we can make some assumption and say that there is the first peak on the right, the lower energy peak that we can assign to water molecule having a high correlation with the environment. There is an intermediate peak, the second peak, and the third one that are molecules that are poorly connected. There are no more assumptions on this. This is just a way to describe our system. And what we see, come back to the Van 't Hoff plot of room temperature water, we find that we can experimentally measure the energy gap between the two phases. It corresponds more or less with the energy gap that has been foreseen by the quantum electromechanical calculation. So there is a good probability that the two phases that we are talking about are exactly the two phases that have been foreseen by the quantum mechanic. Now come to the solution, the effect of solutes on this description of water, and why it's so important to have a deconvolution like the one I showed you before. Okay, if we look at the effect of chlorides in water on changing the concentration, we can see that isosbestic points appear even in this case. These are the four salts or chloride salts. What does it mean? What is the physical meaning of this isosbestic point? There is also another feature that is very interesting. If we look exactly at the center of each subband, we can observe that there is a shift, a red shift, blue shift in the low energy fraction, and the opposite in the other one. So there is a movement. It means that the OH bond length are changing, because these are the vibration of the OH bond, intramolecular OH bond. So expanding differently depending on their assignment, depending on their position in energy, the energy content. So we can try to make some calculation about the data. And if I plot the area that are under the peaks, I show you. Oops. These three peaks. I calculate the three area just in order to have an idea of the number of molecules which belongs to each of one of the three different subbands. I calculate the area and I plot the area, and I discover that in case of the first peak, for the moment let me call it first peak, the first, the second, and third. Then we'll see what actually they are. In the first peak, the area always decreases when I have the salts. In the second and third peaks, the area increases, always increases in case of chlorides. So there is a different behavior. So this means that molecules don't behave the same way. So they are not the same. They are not described by the same physics with respect to solution of salts. And what is much more interesting to me is the effect of salts on the OH bond length, intramolecular OH bond length. So the bond length in the first peak always decreases. In the second, it stays more or less around zero. In the third peak, it increases. So something different is happening in the two populations. So since our system is a superposition of two components, and the third component's assignment is quite complicated and is not clear, at the moment is not clear to me a correct assignment of the intermediate peak. Because sometimes it behaves like the first, sometimes it behaves like the second peak. So we need to work harder to know. But at this point, we can really understand the meaning, the physical meaning of the isosbestic point, because the isosbestic point separates the two phases in water which behave differently with respect to the solution of ions. So there is one phase which shrinks the bond, another one that expands the bond. There is one that decreases, another one that increases. And their absorption crosses exactly at the isosbestic point. But we can do something more analyzing this data. We can have a proof, a direct proof of self-similarity in water structure. We can introduce a deformation parameter. This is just arbitrary parameter. That is the ratio between the area above and below the isosbestic point. The E2 is the blue, E1 is red, but it's arbitrary. And if I plot this deformation parameter for chlorides on changing the molarity, in such a case we have molarity in two different, for two decays, and we do this kind of plot. we can see that the behavior is well described by a sigmoid. So there is a plateau region in which the water doesn't deform at all, very low. After a certain concentration, it starts a deformation that looks like linear, and then there is another plateau region. Of course, the second plateau region corresponds to the maximum of solubility. So it's not a physical region, but you can see that it's not reached because experimentally it's not explorable. The first region is the region where the by description of solutes hold. That is the region where the molarity is below, is about 0.1, 0.2. It's a low molarity solution that are well described by the normal description we have of the solution holds in this phase. But after a certain concentration, something new happens, and water starts to organize in a way that is very peculiar. Because if we look at just the linear part of those curves, we can observe that there is a log-log, they are linear in a log-log scale. This is very important because the straight line fitting the data can be basically represented by that equation, which show that it's a scale-free law. It means that the organization of water is described by a scale-free law. So it's a kind of fractals. The organization of water at large scale behaves in a very special way. And such relationships show the self-similarity property of the system, and we can also calculate the fractal dimension of this behavior. And the fractal dimension is the same for all the ions. So there is something that is not related to the electrostatic, I mean to the ratio charge on mass that usually describe the interaction in short scale interaction. It's something different. It doesn't depend on the kind of water or kind of ions, but it depends on water. It's related to the structure of water. So scale-free networks are very interesting and very important because they have a meaning that is scale-free. Law describes not only physical system, but even biological system, sociological system, political system, economic system, and so on. Are very particular. So it is not a way to define the organization of a system. It's a completely different organization of the system that can be reduced to the normal organization of a system. In fact, the exponential organization of a system is described by a probability that is a Gaussian. In case of scale-free organization, the description of the probability is completely different. It implies that in water there are hubs. In scale-free networks, self-correlated networks, there is the presence of hubs. A single molecule in exponential organization, a single molecule is related only to another one. In a scale-free model, a single molecule can behave like a hub that is related to many more other molecules. This makes the system very robust and very resilient to external perturbation. This is very important in order to understand why water is so related to life, to biology. In fact, it has been found that even in biology, there are molecules that are like water, that are involved in many biochemical reactions. They are very crucial point in the description of the system. So in random network, hubs, in scale-free network, there are hubs. And water shows that it behaves like a scale-free network in a very clear way. So this is to say that self-similarity is very important in nature. It is used normally in nature to form complex systems. Natural complex systems are always described by self-similarity. And auto-organization is something that is completely new. It is not something that appears when the system overcomes a certain threshold of complexity. It's something that is intrinsical to the system itself. And there is something more behind this. There is a mathematical theorem that shows that Giuseppe Vitiello, that is an Italian theoretical physicist, has shown shown this theorem that shows that the self-similarity is always related, mathematically related, to the appearance of coherent system, quantum coherent system, because the mathematics which describe the self-similar system is the same which describe the quantum coherent, the quantum function. So this shows that there is the system, the water organization, long-scale water organization, should be described in a quantum system. It's not a classical system, but it's a quantum system. And this can be obtained even starting from very simple experimental data as vibrational spectroscopy. So, come to the conclusion. The ATR infrared spectroscopy allows to get many information about the intermolecular structure of water. We found that the isosbestic point presence is very crucial in understanding what is actually happening. And so we proposed this kind of data convolution with 3 Gaussians because, I repeat, is the minimum, so mathematically speaking is the best that we can do using the minimum number of subsystems, and because it explained somehow goes in the same way as it has been proved in the realm of quantum electrodynamics. That has something that is being proposed by Emilio Del Giudice and Giuliano Preparata, 2 theoretical Italian physicists, which have shown that water can be described in a completely different way. Up to this moment, it has been very difficult to give an experimental support to their theory because people didn't know what to measure to support their theory. In my view, simple, I repeat, a very simple technique as the infrared spectroscopy can give a strong support to their theory because we can measure, we can observe, and we can have a quantitative explanation of their prediction. And moreover, this technique is very useful to study solution of sols, and we can understand something more about the solvation, because actually we didn't know how the solvation, how does it works, because it's very complicated. But we see that in water there are molecules which solvate in different ways. We observe 2 different ways. Molecules can, do they interact the same way with anion and cations, or there is a difference? The 2 populations I show you, the 3 populations that I show you, interact the same way with anion and cations or not? Why one of the population reduce the OH bond length and the other one expand it? There is probably something behind. This is what we hope to understand in the future with the help of everybody that are here in this room. Thank you.
Any questions, comments?
Thank you, Antonella, for your very precise and clear presentation. Let me say that if someone wants to deepen this aspect, we have the poster number 11 here. But let me ask, can you clarify a little better the 2 fact that we have 2 phases, but it's not about actually, but you needed 3 oscillators in the convolution, just to make a little bit clearer for other, which is the 3rd oscillator. Thank you.
No, actually, we are still thinking about the third component. We just know that there are 3 because of the mathematical requirement. We need 3 subbands to have a good deconvolution. We start from a theory which foresees two different phases in water. So the third may be an intermediate phase in spatial, with spatial meaning. I mean, it should involve molecules which are at the border of the two phases. So, or there can be, we have also to think that when we do spectroscopy, we are looking at the system with making a snapshot which has the duration of the interaction of light with our system. So in case of the interaction of the infrared light with system, we are just looking at the system in a very quick way. That is the time of interaction at 10 to minus 14 seconds. So we are looking, the view that we have is very fast. So is it possible that the time of observation is lower than the lifetime of the state? So in this case, we can also see molecules which are going from one state to another one. This is one possibility. This, of course, is not the only one. There could be also a spatial, molecules which are at the border of one phase on the other, in a spatial meaning, I mean. But this is what we need to know. We need to know better. But at the moment, I hope that the answer to this problem will come to the study of the solution, because we can see that even the intermediate peak, the second peak, change differently when we dissolve salts inside, and it depends on the kind of salts or the shape. So it gives more information.
Just one. This morning, Professor Fumaguchi was talking about having, in this water that we drink, having ice and water at the same time. I always say, out of my experiments and everything I know until now, I think that in this water there is a vapor as well. Now, you always talk about liquid water with liquid phase and ice, but what is vapor? Do we have an idea what is the structure of the vapor?
Yeah, there should be vapor. You mean tiny bubble, nanobubble of vapor?
We have a spectra of the vapor, and this spectra of the vapor covers the spectra of the bulk water, which means that they are exactly at your small peak
The third small one.
Is this exactly this place is vapor.
Yeah, this is one possibility. But when we do the solution, we see that the area of those peaks increases when you have solutes. This doesn't fit with the possibility that is vapor. Why vapor should be affected by the solution of salts?
I think this is very interesting to challenge us.
Yeah, it's not clear. We are just at the beginning.
Thank you very much.
Okay, thank you again. So let's move to the next talk. We will